We do build machine learning technologies. I'm a part of the Machine Learning Research and Development Group at LinkedIn, where I focus on problems relating to news relevance and graph structure. Part of the work that we're engaged in looks at how information moves through social networks and how we can leverage the structure of these graphs to reveal features that are useful for predicting what people need to know to be more productive and successful. So this is an example of some work I'm involved with an amazing team of researchers from Indiana University, my alma mater. YY is leading on that side of the house, and this is a network of organizations, and we draw an edge between two nodes if a person moves from organization A to organization B. And you can see in this graph this nested hierarchical cluster structure. And you see this fine-grained, topically and geospatially concentrated community structure emerge through this hierarchy. And so part of my work deals with how can we leverage the structure of graphs like this to inform news relevance and just a variety of different machine learning algorithms. And this is not going to be the focus of the talk today. So in the spirit of today's piece, I think we're going to talk a little bit about what's challenging about work in these kinds of spaces, and along 4 different dimensions. So first, we're going to talk a little bit about how to operationalize problems in novel domains. And so this is, a lot of these research questions deal with things that are not well developed in the literature, and where there's maybe not a clear playbook in the practice for how to approach a problem. We'll talk a little bit about how to evaluate results from these problems that aren't necessarily crisply defined. And we'll look at how to evangelize and get buy-in once you've built a technology, how to make sure that it sees the light of day. And kind of bookend the whole piece with some thoughts on productionizing these models and some of the more technical challenges that just keep me up at night. So we'll start with problems. I think that there are, broadly speaking, 2 kinds of machine learning problems. The first has this character of having a really clear response variable that is totally unambiguous in its definition. We understand what we mean when we're talking about whether or not a user clicks on an ad. Either this happened or it didn't. This binary response variable is totally unambiguous. If I build a model that predicts housing prices, and my model underestimates the true value of a home, that error term is totally clear. I've lost money. Likewise, if we're doing classification, which species of flower we're talking about, there may be some overlap between the classes, and the decision criteria may be difficult to suss out, but the actual species of the flower is pretty clear to us. And so this is one class of problems that there's a lot of value you can build on the back of these, but more often, the interesting problems have a somewhat less well-defined character. And I think we heard in this morning's panel this idea of, what do we mean by fraud? Like, is this fraudulent? Is this not fraudulent? Can we crisply define what that looks like? I think we come across these kinds of problems, and they're often really at the heart of what we want to do. We want to automate things like expertise prediction. I want to know how good are you at your job. I want you to give me news that I didn't even know I wanted to read. How do I know if I can trust somebody? Is this someone I want to work with? What is the valence of this article? These are all sort of essentially human tasks, and we'd love to be able to automate them at scale. But they all have the character of being, there's some common themes that emerge when we look at ill-defined problem statements like this that really are more of a discussion than a concrete variable. We're talking about qualitative features. You and I may reasonably disagree about the true meaning or the true sentiment of a product review. They're often multidimensional. Expertise has many different dimensions. The vice president of a machine learning research org, is he an expert or is she an expert at machine learning? A person who's a statistician but doesn't have any engineering experience, is this person an expert at machine learning? It's subtle, and we can have a discussion about it. And finally, they're often non-Euclidean. So if you think about trust, I can trust you, and you can trust your colleague, but I don't necessarily trust your colleague. And this intransitivity of trust violates the triangle inequality that is one of these fundamental presuppositions of metric spaces. And many of the models that we use assume a metric embedding of points. And that we just know that for language and things like social phenomena, that's not necessarily a clean representation of the problem. All the same, we have to move on with our lives. And I love this quote from statistician George Box that all models are wrong, but some are useful. The question is not can we do this, but how do we operationalize this problem statement in a way that'll let us build a minimum viable algorithm where we can get a foothold in product and then begin to iterate and design into the product experiences that will let us instrument the data that we're really interested in. And so I think about this in terms of high-fidelity proxy variables. So consider, for example, this problem of trust. Imagine that LinkedIn had an introduction platform. We don't, but imagine that we did. If I introduce two of my colleagues, that's a signal that I trust these people. I care about them in a special way, and I want to create value for them. That's not the thing itself. That's not exactly trust, but it's a correlate of trust. And I can use that as a response variable to train a model, and it may have low coverage. Few people on the platform might use the introductions product, but we can use that small subset to try to build a model that generalizes to hundreds of millions of people. Crowdsourcing is an effective technique for some kinds of problems, but you're always going to want to compare the take a test run on your team. If the 6 of you can't agree on the true class of 100 test examples, people who are being paid $3 and $5 an hour are not going to focus harder than you. But the whole concept is to get a toehold in product so you can begin to iterate and build the thing that you're really interested in. So what I'm not going to talk about in this talk is execution. So I think that building these models and refining the statistical structure of some of these models can be somewhat straightforward. Reducing error terms, the kinds of feature transformations, for example, for heavy-tailed features. There's kind of a playbook in a way. And I think M.C. Escher, when he talked about the hardest part of his work, had something similar to say in the sense that he was trained as a technical illustrator. And the hardest part of the most stymieing part of his craft was not executing on the drawing itself, but rather transmitting that first sketch to paper where he had in his mind a picture of an impossible reality. And the framework on the page was the hard part, getting the broad strokes of a picture, and then filling in the lines and details was just rote. And I think that it's something similar can be said about machine learning technologies. So we'll skip that part and instead move on to evaluation. We now have fit an accurate model that predicts quite well the response variable that we've chosen to instrument the phenomenon under question. The problem is that scale is the essential promise of machine learning technologies. We want to automate things that, we want to automate predictions at a scale that would be impossible for any one human to exact or comprehend. And so now that I have 350 million plus predictions, how do I know whether or not I've done my job well, even though the model is accurate? And so I like to use a technique that allows us to move through a spectrum of response variables where we make predictions. Let's, for example, say expertise. And I want to say, what does the spectrum of expertise look like in the way that I've constructed this model? And so you can take representative samples from quantiles along that distribution and say the people at the top of the distribution are these true positives, the people at the bottom of this distribution are these true negatives, and how does the qualitative character of my predictions change over the course of that response variable? And the question is then, have I well instrumented the thing that I was trying to measure? And so I think that this is a very useful technique. I guess you must have had a slightly older version of this slide deck. This is similar to something Richard Dawkins did, where the idea is that you have a genetic algorithm that allows you to select which of these little bugs I like, and these are being procedurally generated. The objective function is aesthetic beauty. And you take the genes of one of these biomorphs and you mix them, and you can iterate on this. If you Google for this, you can play with this app. You can control the aesthetic character of these little bugs using a genetic algorithm. And so the response function is beauty. And we're iterating on response functions. We have an ill-defined problem statement, but we want to maybe choose a new response variable based on looking at that spectrum of representative samples. I don't necessarily get the quantity that I'm actually interested in. And so as part of this process, there's some things that we need to be aware of. So we may make excellent news recommendations for people in the tech industry, and we may make terrible recommendations for people in the ranching industry. And so being aware of that and making sure that you don't oversample on people who are like yourself is super important, because the quality of the predictions is not going to be uniform across different cohorts. Additionally, it's important for some of these things, like news relevance, to get a sense of how these recommendations change in time. And so I'll talk a little bit later about how we approach that problem. One of the things that you have to avoid at all cost is this idea of simply because a recommendation works for my colleagues does not mean that it is generally good. Employees of LinkedIn are exceptionally engaged in the platform, have robust and complete profiles and dense social graphs. If a recommendation algorithm doesn't work for employees of LinkedIn, it's not going to work in general. So it's important to look at people outside of your social cohort, outside of the Bay Area, outside of tech, outside of even skilled knowledge work, and see how does the qualitative character of these recommendations change for other types of people. So once you've built an algorithm, or in the process of building an algorithm, it's important to get buy-in. And I think that this is one of these challenging problems in the sense that it's really a propaganda campaign of sorts. You're trying to win the hearts and minds of the people around you so that your work sees the light of day. And so I think that along that spectrum of evangelism, there are some lightweight techniques that I like to employ. So I think I try to take meetings early and often with the people who may not be directly involved with developing the algorithm, but who are going to be in the mix as we try to move it through to production and ultimately to consumers. So developing a narrative frame saying, this is what we're talking about. This is the way to think about it. Our algorithm is this, and it's not this, helps people understand your work, and it keeps it top of mind. So actively taking meetings throughout the product development process, I think, is important. Additionally, giving a person a toy example to help them understand the thing that you're doing. And I think that the analogy that I use for trust, where I trust you, you trust your colleague, I don't necessarily trust your colleague, is a good example of this. It's as simple as possible, but it very crisply captures this property of non-transitivity. And so now a product manager can go and use that example when they talk about the work. And likewise, if we're using a decision tree, what's the minimum example, the minimum structure that gets across the essence of the algorithm? I think that this is very useful in the sense that it makes it less of a black box, and it makes it much clearer to your colleagues how to think about what the algorithm is doing, and that gives them a sense of agency. Finally, I think scheduling, or even just on a manual basis, but scheduled emails are nice, sending out example results on a weekly cadence or a daily cadence saying, hey, here's what our news algorithm thinks is relevant in these 5 industries. Here are the top 3 articles today. That keeps things top of mind, and it gives you a sense for how this evolves in time. What's more, you get feedback on the quality of your results, and you'll see things through other people's eyes, and it gives them a sense of buy-in, and they see their thinking reflected in the thing itself, which gives them a reason to advocate for your work. I think that's very powerful. There's also, so this is kind of on the very lightweight end. We might just, batch out, hit HDFS and batch out the most recent results, send those out in a weekly email. With regards to building somewhat more robust infrastructure, I think notebooks like Python notebooks, are an especially effective way to communicate with technical partners. So you can, for example, have a notebook that allows you to look at the statistical structure of various models and say, okay, I want to choose, I want to do a side-by-side comparison of these 2 different models and see what do their precision recall plots look like, what do the feature distributions look like, how many records are we training on. This is a very natural way to communicate with your engineering partners. I think additionally, a useful exercise is building really lightweight web applications. So this is, a Django or a Rails web app that lives on a machine in the intranet, for example, that connects to a key value store, and it pulls the latest results, and it lets you select, for example, from a dropdown and see the results of 2 models side by side. And so this lets non-technical partners share something over email and say, hey, here's the link, this is what we're doing, this is what our people are working on. And it makes it really easy for a person to engage and to begin to see how this might look in production. It also gives you the ability to control the sort of mind space in terms of design and like use cases, because you can just change how the web app looks. And that instills in a person's mind this idea of, oh, now I understand what we're going to be doing with this. And finally, when you're actually building the product, it's important to make sure that you bake in from the very start the ability to rapidly prototype in product with your team. So this is not necessarily A/B testing, but rather the ability to launch new algorithms to an internal audience in the actual product itself, so that you can see the predictions in the context of the ecosystem at large. Because you might see, wow, like this looked okay on its own, but it really doesn't meet the quality bar for these other recommendations. Or it could blow it out of the water, but there's a gestalt in which the sum is more than the whole is more than the sum of the parts, and I think it's important to see the recommendations in context of live product. So I'll spend the last few minutes here talking about some of the issues that I think many of us face when it comes to productionizing these models. And you can see these Byzantine systems being built, and I don't think that this is a solved problem. And it's an interesting engineering problem. In the best case scenario, we'll talk about something simple like logistic regression, where we have a beta vector of feature coefficients. And there's sort of two sides, there are two ends of this spectrum. On one end, you have distributed fitting, where you're having hundreds of millions of records spun out to many, many worker nodes, and you're fitting a model on the grid. This is nice because your feature transformations, your feature generation pipeline, your training, and your predictions all tend to live in the same ecosystem. They're in the same language. Your production environment is the same as your training environment. The problem here is that this is slow and often difficult to debug. And there are drawbacks. There are benefits and there are drawbacks to this approach. Another world is one in which we're fitting a model locally on a development machine. Often with these high fidelity proxy variables, we just have 5 or 10 million records that we're trying to train the model on. And even as we see the cardinality of that data set increase, we don't see a change in the coefficients we're fitting. And so it's fine to fit it on a local machine. Very fast, very easy to iterate. The problem is we now have the same thing living in 2 different places, and sometimes in different languages. And this is just, it's kind of I want to say cluster, but I'm not going to. It's a bad situation. We have feature transformations. It's a bad situation. So we get into this situation where you have, I need to make sure that if I'm taking the logarithm of a heavy-tailed distribution, I need to make sure that the base in production of that logarithm is the same as I'm using on my local machine. If there's this question of model specification. How do I communicate the structure of the model to the production environment? Am I copying coefficients from a text file? This introduces transcription errors. Am I batching, how am I implementing the linear combination? Am I using a different library in production? Am I writing my own iterator through a map? It's not clear how to make isomorphic the structure of the model locally and the structure of the model in a production environment. And I think this is an open problem. I know that this is an open problem. PMML, for example, does not solve it. This is the best case scenario. I think it gets much more challenging when we're talking about something like a topic model or something sophisticated like a decision tree. Like I've seen, Weka allows you to generate Java objects that encapsulate the logical structure of a decision tree. I've seen those Weka text files in production environments. It's not a great path to prod. I want to walk you through an example from a product I worked on a while ago, where one of the pieces of the puzzle was doing member-member similarity calculations. And so one of the things you might do there is look at a matrix of member by skill and want to compare people in terms of the skills that they have. Often it makes sense with a sparse matrix like this to decompose it into a low rank approximation of the original matrix. So we're talking here about the singular value decomposition, by way of latent semantic analysis. So we implement this in GenSim locally on a matrix that's reasonably small, on the order of a couple million rows. And the results are great. We can say, okay, who are the people that are most similar to this member? What's the cosine similarity score for these two people in the eigenskill space? We know that it should work. To get this into production, we essentially have a situation where that left singular matrix is the structure of our model, because I fit on, let's say, 5 million people. But now I need to generalize that to 350 million people. So I need to project new vectors into that eigenspace. And so I multiply a member skill vector by that left singular matrix to get their position in this reduced dimensionality space. So this left singular matrix is the structure of the model. And so what we did is we serialized that matrix, packaged it with the Hadoop jar, loaded it onto HDFS using a pig script, loaded it into the distributed cache, had a Java UDF that would call it from the distributed cache, so it's resident in memory on all of the mapper nodes, and then pass that member skill vector from a pig script into the Java UDF, multiply the two matrices, and get back the eigenskill representation of that member. Push that to a key value store, have another service call the key value store, which says, I need this member, implement cosine similarity at the service side, and now I have a result. I come to you and I say, hey, the results in prod for cosine similarity aren't the same as the ones we're getting out of GenSim. Where do you start debugging this pipeline? It's structurally tough, and I don't think that these models have enough in common that there is a clear way to have the, like something like predictive markup modeling language, or predictive modeling markup language, where it is the one-size-fits-all platform that can be used as an interchange format. I think that, and I'm hoping Pete's going to drink now, that Spark and MLlib and cheers, coffee crystals, right? The notebooks that let you look at the features, distributions in an interactive way, you can fit on a small training data set, you can fit on a large training data set using the same API and frameworks. I think that that's a very powerful model, and it's obviously I think there's a lot of traction behind that. But I think that there are still a lot of open problems in this space. And so these are some of the things that I think about when I think about what's hard about this work. And I don't know that we're ever going to have easy answers. I think that this is the essential value of experience and persistence, is that you just hammer on the thing until you have the quantity that you want to measure. And you're not, this minimum viable algorithm that gets you a foothold in production, that's not going to be the thing itself. And I think, I learned a lot of this from Pete, and this idea of skills, like scraping profiles to get a skills representation that you can then build endorsements on top of, that you can then build other systems on top of. You start small and iterate. And so when I think about building machine learning algorithms, that's where my mind is how can I get a system that will let me collect the data that I want and that will put the hard part of the computation, which is, do I trust this person? Do I believe this person's an expert? You want to embed that stuff in human brains rather than the computer, and then instrument at scale the judgments of humans to do a better job of predicting the thing that you care about. So those are some of the things I've been thinking about. Thanks for taking the time to share them with me. Daniel, what's up, man?
So I love the example. I'm glad you're allowed to talk about it of that crazy pipeline. I'm curious, looking back, with the virtue of hindsight, what do you imagine you might have done differently to have been in a better position to get when you got to that debugging situation?
I'm sorry, can you?
Well, so I mean, as you described it, and I'm not going to try to reproduce the 15 or 16 steps, right? But knowing now that you got there, starting from that same point again, is there a different path that you might have taken that would have put you in a better position, maybe not with the best results, but with that debuggability that you wanted?
Yeah, I mean, I think we've started doing a lot more unit testing. I think from a tooling perspective, like pig unit testing has gotten a lot cleaner, and I think that percolating through, I mean, obviously in the ML research group, SNA, there's a strong engineering culture, and so I think that like the lesson that I've most like sort of internalized with regards to this is that data science is engineering, and it is building robust productionized systems that give you clear visibility on what's like logging and unit testing. I think just doing that step by step through the pipeline kind of makes it much clearer that, well, we know we're not going off the rails when we're computing cosine similarity because that's been tested. So I think testing is a big part of that. Mm-hmm. So maybe I don't understand the question. Yeah. So the question is like, how do you handle misclassifications, like false negatives? So I think the like confirm or deny approach is, you know, and you can look at what we do with endorsements. You say like, do you think that you want to endorse this person for this skill? It's like, I have an intuition that this might be the case, but I'm going to ask you. And I think that's a pretty powerful mechanism where like people you may know does the same thing. It's like, here are 30 people. I don't need to get great precision here. You know, it's like I'm not freaking out if the third one isn't somebody I know, but it's fine if the fourth person is. And so I think that's a lot of it is making sure that the people are still in the loop. And we talk about human-in-the-loop computing, and I think you present it and then allow the end user to make a decision. So I think that's probably our time.
Great. Thank you, Mike.
Thank you.
Thank you.